welcome to this presentation on plasma in the kitchen. This presentation was made by, I think in the next slide, uh, Dr. Vladimir Kolobov, a research professor at CSPAR and also engineer at CFDRC, um, Santi, a GRA student, and myself, Juan, also a GRA student at the Space Science Department in the University of Alabama in Huntsville. So in this next slide, you'll see um, a bit of a table of contents, I guess. So we're going to start by, or I'm going to start by giving you a brief introduction to modern plasma technologies. Then we're going to go sort of to the basics and look at what happens inside a gas tube when you apply a voltage across it. And then we're going to get a little bit more technical and look into plasma sources for semiconductor manufacturing and material processing. And we're going to come full circle and come back to the kitchen, tell you a little bit about how you can do your own experiments of generating plasma with a microwave oven and a few other household supplies. Moving into a brief introduction to modern plasma technologies, um, the first thing I'll say is when you think of plasma as the fourth state of matter and consider that it's supposed to be this ionized gas and the stuff stars are made of, you may wonder if plasmas are really relevant to our everyday life. And of course they are, but not just because every ecosystem in our planet pretty much relies on the sun's energy to survive, and the sun is made of plasma. But you actually need to look no further than your own kitchen to spot several things that you use perhaps every day that either need plasma to work or were manufactured using plasma. So let's start by saying if you still have a plasma display TV in your living room, or perhaps compact fluorescent lamps lighting anywhere in your house, then you indeed use plasma on a daily basis. And I should mention that these devices are now being replaced by LEDs and more energy efficient technologies. But these work by applying a high voltage to ionize a low pressure gaseous mixture, typically some noble gases and mercury. Um, this gaseous mixture is relatively cold, about room temperature, and the electrons in this mixture are actually hot. They're about a few electrovolts in energy. And these hot electrons actually excite atoms to produce photons, which then hit a phosphorus coating that transform the UV energy from the emitted photons into a less energetic visible energy. And this is the fluorescent lamps that you could describe as a white light, or in a plasma display, it's specific colors for each of the pixels. You may also have a water or air purification device in your kitchen that is based on plasma. These devices use plasma to create ozone, which, when diffused into water, will oxidize contaminants and kill harmful bacteria, render metal compounds insoluble, making the air and the water safe to consume. Um, Also, if you store any medicines in your kitchen, then there's a good chance these were manufactured using air or argon plasmas used as sort of beams to sterilize the surface on which the medicine was produced. And if we're willing to expand our search for plasma technologies to anything that was manufactured using plasma, then you're going to see plasma everywhere. And a lot of the items that I'm listing, I should say, are on this slide, numbered 1 through 21, so you can find them. Um, Plasma enhanced chemical vapor deposition, for example, works by utilizing an ionized gas at low or even atmospheric pressures to induce polymerization, that's bonding, of certain chemical species called monomers onto a surface, thereby creating a thin coating. And this technique is present in the manufacturing of many products like eyeglasses, liquid crystal displays, solar panels, diffusion barriers for food-safe containers. Um, Other materials like polymers or textiles can be treated using plasma systems in order to improve their surface properties. Um, and all of this talk about using plasma in our food and our delicate textiles might seem like maybe we're using a more mild subclass of plasmas, perhaps. But we also use plasmas in a pretty aggressive manner in certain manufacturing processes. For example, ions in a plasma chamber are energized and driven towards a target using a powerful electromagnetic field to obtain certain objectives, such as artificial hips or bombarded with ions to improve their wear, friction, and corrosion properties. Window glass can be made more energy efficient by sputtering it with metal particles dislodged from a target being eroded by the ions. In other applications, plasmas are treated almost like lightsabers. They're used to disinfect or cut surfaces, um, such as in the production of heart stents, laser cut cloth or metal, and processed microelectronics. And even outside of the kitchen, you see plasmas in plasma aided combustion and film cooling of jet turbine blades, high intensity discharge lamps on some cars. Definitely a lot of applications, and you can see them without leaving your home. Hopefully, I've managed to convince you that plasmas not only comprise 90% of all visible matter in the universe, but actually surround our daily lives. And Perhaps I've given you some evidence to believe that the disciplines of plasma science and engineering will only grow in popularity and relevance over the next few decades. So on the next slide, we're going to go back to the basics, if you will, and um, look at a very basic experiment. And in fact, you can think of it as the experiment that first created this discipline of studying plasma, um, other than looking at the sun, but say in a laboratory setting. And this is what happens when I take a tube filled with some gas, typically at low pressures, and I apply a voltage um, along the tube from one side of it to the other. Rather complex kinetic and transporting chemical processes take place in this setup. And I'll just basically say that what happens is generally first the electrons are accelerated and heated during this process. Now, the acceleration is usually when the electrons um, are energized in that their movement from one side of the tube to the other increases. And as they collide with other particles, say other electrons or ions or neutral particles, that movement is randomized. And what happens is that increases their um, thermal velocity. And that's what we call heating. So if you think of acceleration and heating as two forms of energization related to movement, whereas the acceleration is an increase in the directed velocity and the heating is an increase in the thermal or random velocity. And these electrons that are, as I said, accelerated and heated, these first electrons we call seed electrons, and they initiate what we call an avalanche ionization process, which results in electrical gas breakdown and plasma formation. And secondary electrons are then generated by the ions impacting the cold cathode. And that seems like a very complicated sort of process, but it happens fairly quickly. And that transient step passes. And then you have a sort of steady state configuration. As you can see here in the image, you have number 1 through 6. These are called the cathode sheath, the negative glow, the Faraday dark space, a transition region, the positive column, and the anode dark space. This positive column gives the name to these types of gas discharges. They're called positive column plasmas. And they received that name because in this region, which tends to be the one that emits the most light, you actually have an increased number density of the ions with respect to the electrons, and that makes that part of the plasma have a positive charge. And so that's why it's called a positive column. This figure also shows spatial distributions of the electric potential, densities of electrons, ions, and excited metastable atoms, electric field, and electron temperature for these type of discharges in a typical argon plasma. So next, we're going to look at what I like to call as rules of thumb, or kind of easy ways to categorize the different regimes of these types of plasmas. And we call those scaling laws. So the discharge characteristics are going to depend on the product, heavily depend on the product between the gas pressure and the interelectrode gap length. We'll let gas pressure be labeled as P and the interelectrode gap length be labeled as D. Then we actually find experimentally that atmospheric pressure discharges, which have typically on the higher end pressures for these type of experiments, with small interelectrode gap lengths, say of the order of 0.1 millimeters, those atmospheric pressure discharges behave very similarly to vacuum discharges that have longer gaps, say on the order of 10 centimeters for the in between the electrons or electrodes, excuse me. And by vacuum, we mean, of course, not a perfect vacuum, but very low pressure, such as a single torr. The dependence of gas breakdown, or the gas breakdown voltage, labeled as U, on the product P times D, is called a Paschen curve. And the Paschen minimum corresponds to the optimal conditions for a static gas breakdown. So for a given gas pressure and interelectrode length, there will be a sort of threshold voltage past which gas breaks down, and you're creating a plasma at this point. And the low P times D values, which are the left of the Paschen curve, correspond to a vacuum breakdown. And on the right branch of the Paschen curve, then you see transitions from a Townsend to a subnormal to a normal to an abnormal discharge taking place. And the so-called normal discharges are characterized by a cathode spot with a normal current density. And this is a good segue into the next slide, which we title Plasma Self-Organization at Material Interfaces. Because a cathode spot is with a normal, and normal I mean, given these regimes, that's all relative to what we're working on, but a normal current density is commonly formed in these Ziegler discharges. And that spot is displayed on the cathode. But plasma self-organization in the anode regions can be a lot more complicated. Beautiful and puzzling structures have been observed on the surface of solid and liquid anodes, such as those that you can see in that picture. And why this happens is actually still a mystery. And that's what we're doing research on, partially trying to understand why these spots appear. And obviously these spots of light being emitted have to do with the ionization of the plasma in these specific regions. And I just personally think they're pretty cool and definitely worth studying. So next, we're going to look at also some of these strange features that develop under specific regimes, such as constriction or stratification of plasmas. Now, constriction is when the emissions in a plasma are constricted to a certain region. Like you can see here in the top left image, how their plasma sort of seems to only be ionized or emit light on the right half or the left half, so close to the anode or the cathode, depending on your conditions. And by stratification, we see in the bottom left that you get these sort of patterns of light, dark, light, dark, light, dark regions. And again, these can be static or moving, and these have to do with what's happening at the molecular level, with the molecules being ionized. And it's actually interesting that until recently, um, we were not able to computationally model these things. These were experimental findings that we could clearly recreate in the lab, but we were unsure of why they happened. And only recently have good computational models replicated this behavior, and we have a better understanding of these phenomena. But there's still a lot of research to be done, certainly. The next slide is briefly going to, oh, I'm sorry, there was here are some of the computational um, models here, and you can see the moving striations. Um, so at least qualitatively, they clearly match this image on the left um, for an experimental setup. But the next slide is just briefly talking about plasma-aided semiconductor manufacturing. And this is, okay, this is all nice of using cathode tubes or vacuum tubes with a cathode and an anode. And research-wise, they're very interesting. But in terms of application, they're not, I guess, complicated enough to really be used in manufacturing directly. So what usually when you are going to use plasma in manufacturing, you have these complicated setups, like you can see here in the any of these pictures really. And so those systems are a lot more difficult, and there's a lot more physics and chemistry that goes into them. So you need to have a part of your simulation that models plasma production, then another part that models surface processes, and those two have to be coupled. And then you have to have solvers that account for the different scales in your system, and that adapt to the surface morphology. So definitely very complicated matter. But I also think because it's complicated that there's a lot of work that can be done, and there's a lot of interesting features to study, and sort of never run out of things to look into. So next, we're going to look at specifically inductively coupled plasmas and capacitively coupled plasmas. So first, inductively coupled plasmas. On the left here, you see another figure of a model, a computational model for a device here that generates inductively coupled plasma. So inductively coupled plasma is produced by applying a radio frequency current to a coil, and this current induces a time-varying magnetic field around the coil, which penetrates through a dielectric window inside a vacuum chamber. The time-varying magnetic field induces an electric field according to Faraday's law, and the electric field heats plasma electrons, which initiate chemical reactions and maintain the ionization process. The gas mixtures used in plasma processing vary, and they include rare gases, fluorocarbon plasmas, silane for the deposition of silicon dioxide, hydrocarbon plasmas, etc. And like I mentioned here, this is this was a computer simulation used for the design and optimization of a real system. And I'm not sure if you can see it or if it's included in this model, but the simulations also clarify how the electromagnetic power penetrates into plasma within a skin layer near the radio frequency coil to get absorbed by the electrons inside the skin layer. Now, by skin layer here, we refer to the phenomena by which electromagnetic radiation penetrates only so far into conductors. This happens because the electromagnetic radiation induces alternating currents um, in the conductor, and those currents actually work to shield the um, incoming electromagnetic radiation, and that a normal electromagnetic skin effect would have a decaying exponential power law for the electromagnetic field penetrating so deep into the conductor. So it penetrates at the very surface and then exponentially decays until it's basically non-existent at a certain depth, and that's what we call the skin effect. And taking into account more complex heating processes and transport processes for electrons, you can get a what we call anomalous skin effect in plasmas. And these simulations, these systems, as you can imagine, they're very difficult to analyze on paper. So we kind of need reliable simulations and computational resources to clarify these effects and study them without having to spend millions of dollars in building the machine ourselves and then potentially breaking it because we use the wrong conditions. So modeling or simulation is definitely an important part of the entire process. Um, Next, we're going to look at capacitively coupled plasmas. And radio frequency capacitively coupled plasmas are widely used in dry etching of thin films and plasma enhanced chemical vapor deposition, which I mentioned earlier as manufacturing a lot of different things for our daily use. Um, Specifically for semiconductor equipment and flat panel display industries, they use these very large area, or they need to create kind of large area panels, so say on the order of a meter by a meter glass panels. Um, and these capacitively coupled devices or setups operate at very high frequencies like 200 megahertz to ensure efficient power coupling to electrons. In order to model this, we have to solve Poisson's equation for accounting for the electric field in the discharges. Uh, you can see that the discharge here consists of a oscillating sheets near the electrons and a sort of quasi-neutral bulk plasma between the sheets. It's also interesting to see how the electrons respond almost instantaneously to the electric field oscillations, whereas the ions respond more slowly to a radio frequency period averaged version of the electric fields. Um, and before I get lost in the weeds here of talking about the details of this, I'll go ahead and skip over to the last slide in which we wrap this up by going back to the kitchen and telling you how you can do your own experiments of generating plasma using just a microwave and a few other commonly found in your house supplies. So you can make plasma in your kitchen, and before you laugh at me because this seems silly, this inexpensive method for generating plasma has actually been the focus of several published papers, and I leave the link for one in the slides. Now, if you know how a microwave works, it works by um, running a electromagnetic field through the microwave that's supposed to make polar molecules, usually being water, in your food oscillate. And these molecules that start oscillating bump into other molecules and collide and dissipate that energy that was given to them by the field in the form of heat. Now, if you put something in the microwave that is at a very low pressure, then as those molecules start oscillating, they're not going to have, call it a lot of neighbors nearby, other atoms and molecules to collide into to release that energy and convert it from acceleration into heating. And what's going to happen is that eventually they're going to accelerate enough that the the electrons and the ions are going to have opposite torques acting on them, and they're just going to rip apart. And those first electrons, those seed electrons, are then going to bump into other atoms and generate ionization avalanche. And by this point, this should sound familiar. This is now going to realize a gas breakdown in your electrical gas breakdown in your whatever vacuum you have in your microwave and generate a plasma, and you'll see a glow, and it'll look sort of like a gas discharge tube. I should say, please do this with an old microwave. It's not your main kitchen microwave, and do it at your risk. Take precautions. I leave there in the at the very bottom a YouTube link to somebody who's done this before, and you can see sort of what happens to know what to expect. And with the first question is, why is the positive column in a gas discharge called the positive column? The next question is, what is the difference between acceleration and heating? And the last question is, what is the skin effect? All right, and with that, I'll say thank you for your attention, and stay tuned for the next presentation on lightning, sprites, and elves. How are these related to plasma?
Hi, my name is Plasmy, and thank you for watching this video. Make sure to follow us on our social media at CPU2AL on Facebook, LinkedIn, and Instagram. Bye!